So now we are going to consider particle and electromagnetic field. Okay, particle and electromagnetic field. Now, just a reminder that we have the magnetic field, which can be expressed through the vector potential in this form. It's a curled vector potential. And we have electric field, which we can express as a gradient of the scalar potential and the time derivative of a vector potential. In relativity, this equation hold, but I'm not going to touch the relativity here. I'm just the reminder for the curious. Okay, so now my claim is that the Lagrangian for an electrically charged particle in this electromagnetic field can be written in this form. Okay, so we have the kinetic term, that's the usual, minus the potential, and the potential in this case will be written in terms of the scalar potential and the vector potential, which is multiplied by the velocity of the particle. Okay, and times the coupling constant E. Okay, so but how to prove that it's actually the correct Lagrangian? How to show that it's correct Lagrangian? Well, let's find the equations of motion. Okay, and to find the equations of motions, we differentiate dl with respect to dxi, where xi is the component of the vector r, xi dot, and take the derivative ddt. Okay, so, and we subtract dl dxi. Okay, so like the first term, ddt, we get this contribution from dl dx dot I. Okay, so don't forget, so we have xi entering here, xi dot entering here, both of them contribute. Okay, additionally, we will have also the contribution from taking the derivative with respect to xi of L, and this comes about only because these fields are also the functions of R. Okay, so this field is a function of R in A. Okay, is a function of R. Okay, so, and therefore we'll have gradient. So derivative with respect to xi of phi will give us the gradient, and here we'll also have the gradient, but now of a more complex combination. This is this scalar product. Okay. So, but now let's concentrate actually on the first term. In the first term, we have to take the derivative. Okay, we easily can differentiate the first term to get the acceleration. But now, when we differentiate the second term, we have to explicitly remember that the vector potential is a function of the coordinate and time. Okay, so, and therefore, and the coordinate in its own turn does depend on time too. So, and therefore, we need to take care of this. First, explicit depends on time. Okay, here it's written E dta, so we are working with this term. So that's first contribution from here. And then we differentiate with respect to the j's component of the position of the j's component of the position vector x. Okay, and multiply by the velocity x dot j. Okay, so this all together is this term differentiated with respect to time. Very good. So now, additionally, we just rewrite this, and we rewrote that. So now let's combine things together. Okay, when we combine things together, we will have this term together with this term. So this gives us this combination, and then we will combine the terms in front of the velocity. So this term and this term will combine together, and this is what we get. And from the definition of the electric field and from the definition of the magnetic field, we see that the first term is just nothing else but the minus of i's component of electric field, and this combination is nothing else but epsilon ijk times bk. This is a negative sign. This, again, you can prove by considering one of the identities that we had a lot of practice with during the homework 0 or analogous identities. Okay, very good. And therefore, at the end of the day, we ended up with these equations of motion. Okay, these equations of motions. When I brought some pieces here, they entered with a negative sign. I just brought them to the opposite side of this equation, so these negative signs will go away. Okay, so our acceleration here is proportional to the electric field, and it's proportional to this combination over here. Okay, we can simplify it a little bit and write everything in the vector form, and this is how it's going to be, how it's going to look in the vector form. So the second term here is r dot crossed, all right, so vector product with b. Okay, so this is going to be our equation of motion, and you can recognize that indeed that this is the Lorentz force. This is the Lorentz force. The thing that we could have expected from to begin with, and this shows then that this Lagrangian we have chosen appropriately. It indeed reproduces the expected Lorentz force. So by the way, so this Lagrangian has an interesting symmetry. So just a reminder on the gauge symmetry. The gauge symmetry, if you transform the scalar field and the vector field at the same time by following this rule, then electric and magnetic field do not change. Okay, so that's the gauge symmetry. Well, this is kind of interesting because in our case, in the Lagrangian, we have this F and A. So it's kind of strange that by doing this transformation, the Lagrangian shouldn't change, or at least the equation of motion shouldn't change, because the equations of motions depend only on E and B don't change. Okay, but let's see what we get. So we get the Lagrangian, the old Lagrangian. We do this transformation, we get the old Lagrangian from which we started, plus we will get these contributions. But these contributions we can just write as just a derivative with respect to, full derivative with respect to time of chi, which is a function of r, and it in its turn is a function of t, and a function of t, explicit function of t. So we will have this first contribution due to explicit depends on t, and the second contribution is due to the depends on r, which is also a function of t. So, and therefore, our Lagrangian changes by the total derivative, right? By the total derivative. And if it's changed by the total derivative, then the action doesn't change at all, because we can integrate this total derivative, and it will give us the values of this function on at the endpoints, right? So the action will only change by a constant, but the change of the action by a constant is not relevant for our discussion, because when we vary it, the constant will drop out. And that's it. So this is how we show that this Lagrangian is gauge invariant. So we will be returning to this particle in electromagnetic field many times, and we will also solve some of the problems on this, and we will also consider the Hamiltonian formalism. So all of this is pretty important and more or less straightforward, but nonetheless one has to be confident with index notation and this indices transformation and all of that. All right.